Hi there, Mr. Sutton here, bringing you the AB Calculus 5-4 Extra Practice Solutions on RAM Part 1. For this problem, we're trying to approximate the area under this linear function on the interval from -2 to 6 using LRAM. So let me start by setting up a table. And if I'm doing 4 sub-intervals for this distance here, that means I have to be going by 2's for my intervals. So let me just get some table values. I'm going to use the x values -2, 0, 2, 4, and also 6. And I normally would use a calculator to make this table, but in this case I don't think I really need one. So we've got -2 plus 4 is going to be 2. And then since each of these x values is going up by 2, and we have a slope of just 1 here, each of these numbers is going to go up by 2. So we're going to have 4, 6, 8, and finally 10, faster than using a calculator in this case. So now since we're doing LRAM, that means that we need to do the base times the left height in each of these rectangles. So we have a base of 2 times a height of 2, and I'm going to say that my integral of f of x from -2 to 6 is approximately equal to all this stuff. So we've got 2 times 2. Next we have a base of 2 times a height of 4, the left height there, and then a base of 2 times a height of 6, base of 2 times a height of 8. And basically what's going on here, I mean, we could use a calculator to add these together, but what's really going on, you could factor out a 2 from all this, and then you're just doing 2 times 2 plus 4 plus 6 plus 8. So that's really 2 times 20, which just comes out to 40. On this problem, I want to approximate the area under this linear function over 4 subintervals using MRAM on the interval from 2 to 4. So let me start by setting up a table here, and I'm just going to come up with my midpoint x values for this. So if I'm going from 2 to 4 over 4 subintervals, that means each of these subintervals must have a length of 0.5. So the first one is a rectangle going from 2 to 2.5. But the midpoint x value from 2 to 2.5 is 2.25. So that's my first midpoint there. Then the next rectangle goes from 2.5 to 3. The midpoint x value on that is 2.75. And you can see these are just going to go up by 0.5 each time because that's the interval length. So we've got 3.25 and 3.75. And I'm going to go ahead and make a table on my calculator now just to find all these f of x values. So here I am in my calculator. I'm in the y equals, and I've entered my function here as y1. Now I'm going to go to table set, so second window. And I want this to start at 2.25, so 2.25. And then I want the delta table here to be a 0.5 so that these go up by 0.5. And now let me go second, and then I want to do second graph to get table. So here are my y values that go with these. We have 6.125, 6.375, 6.625, and 6.875. So here they are again, just what I got on my calculator. And now I'm going to go ahead and actually add all this together, all the rectangle areas anyway. So because I've already figured out the height at the exact x value I want, there's no decisions to make. It's really just going to be an interval length of 0.5 times all the heights that I put in my table. So I've got 0.5 times 6.125, and I'm going to say integral is approximately equal to what I'm about to write here, because this is an approximation, not an exact value. So to this, we're going to add 0.5 times this next one, 6.375. Plus 0.5 times 6.625, plus 0.5 times 6.875, and let me just add all this up on the calculator. You could leave it unsimplified, but I'll just come up with a final answer here. So just to save me a little time entering this on the calculator, since I noticed that each of these terms has a 0.5 that's being multiplied by another number, I basically just factored out a 0.5, and now I'm adding all the 6 point whatevers inside of parentheses next to it. So pressing enter, that all comes out to exactly 13. So there's my final answer on that one, simplified anyway. On this problem, I'm trying to approximate the area under this linear function using LRAM on an interval from -1 to 1 over 4 subintervals. So let me set up my table of x values that I'm going to be using to come up with my rectangle heights. So since we're going from -1 to 1, and it's LRAM, we're going to need the endpoints for each of the rectangles. So let me start with -1. And then if I'm going a distance of essentially 2 over 4 subintervals, that means each subinterval must be 0.5, so that's the width of my rectangles. So my next number then is -0.5, followed by 0, 0.5, and 1. All right, now I'm just going to use my calculator to plug in all these values to f of x, and I can get the rectangle heights that go with these. So here I am in the y equals of my calculator. I've entered my f of x as y1, and now I'm going to do second window and go to table set. And the way I've set this up, I'm starting my table at -1 and going by increments of 0.5. So that's basically going to give me this table here. And then let me just do second graph to get that table. So at -1, we get an output of 4.5. And after that, we have 4.25, 4, 3.75, and 3.5. So here are just the values that I got off my calculator a second ago. And 3.5 is the last one. So now let me just do the setup using LRAM. I'm going to have the base of each of these rectangles times the left endpoint height of the rectangle. So integral from -1 to 1 of f of x is approximately equal to, and here's our first rectangle, base of 0.5 times a height of 4.5. And again, notice the approximately equals. And then my next rectangle, I have a base of 0.5 still times the height of 4.25. So we're just using the left endpoints of each of these. Then 0.5 times 4. And finally 0.5 times 3.75. And I'll just add all these up on the calculator. To do this efficiently on the calculator, since I noticed that these all have a common base here of 0.5, I basically just factor that out of everything. And inside my parentheses, I'm just adding the left endpoint heights together. So 4.5, 4.25, and so on and so forth. So just adding all that up and multiplying by 0.5, we end up with 8.25 for the estimated area under this curve. For this one, I'm trying to figure out the area under this parabola over the interval from 1 to 3 with 4 subintervals using RRAM. All right, well, let's start by making a table. So since I'm using RRAM or LRAM, both of them, going to require the outer endpoints for each of the rectangles. So we're starting with the x value 1, the left endpoint of the first rectangle. And if I have 4 subintervals over this distance of 2 for the whole interval, that means each subinterval must have a distance of 0.5 if these are equal length, which we're assuming they are. So that means after 1, the next endpoint is 1.5, followed by 2, 2.5, and finally 3. So these are the x values I'm going to plug into this function now just to figure out what the heights of each of these endpoints of the rectangles are going to be. And I'm going to just do this on a table on my calculator. So here I am on the y equals. I've entered my function in y1. And let me just go to second window for table set. I want my table to start actually at +1. And I want to go by 0.5 for my increments so that I get all these numbers for x. And let's just do second graph to get the table. So at the input 1, we have an output of 11. After that, it's 10.75, 10, 8.75, and 7. So we had 11 to 7 all the way over there with some numbers in between that I'm just taking off my calculator and putting them in here so we can look at them. All right, so at this point, it's time to set up our RAM setup with the rectangles being added together. I can say that the integral of f of x from 1 to 3 is going to be approximately equal to the following. So I have a base of 0.5, and I'm using the right endpoint of this rectangle, the height there. So 0.5 times 10.75, that's going to be my first rectangle area. And then I've got 0.5 base times a height of 10, 0.5 times 8.75, so just using the right side of each rectangle, and then 0.5 times 7. And you could leave it unsimplified, or if you wanted, you could add it all up, which I'm going to do now on my calculator. To do this a little more quickly on the calculator, since I have the same base of 0.5 for all of these, I'm just taking 0.5 and multiplying it by the sum of all of these rectangle heights. I basically just factored out a 0.5. So doing that now, we end up with about 18.25. So that's our area using RRAM. On this one, I'm trying to approximate the area under this quadratic function over the interval from -3 to 1 over 4 subintervals using MRAM, the midpoint rectangular approximation. I'm going to start by setting up a table with my x values and the y values that go with them. So since this is midpoint RAM, I need to figure out the endpoints of each rectangle and then use the middle value between those endpoints. So since we're going 4 subintervals over a distance of 4 from -3 to 1, that means each subinterval actually just has a length of 1, which is kind of nice. So I'm going to go halfway through each of these. The first rectangle goes from -3 to -2, so the midpoint x value that we actually have to find the rectangle height at is going to be -2.5. And after that, we have a rectangle from -2 to -1. Midpoint is going to be -1.5. And then you can see these are just going to increase by 1 each time. So -0.5 and +0.5. Next, I need to find the y values that go with all of these. I'm just going to plug these x values into the original function, and I'll just do this on my calculator to save a little bit of time. So I've entered this function in my y equals, and I'm just going to make a table with these x values in it. So let me just go to second table set, second window, and I want to start at the x value -2.5. So let me make sure I've got that in there. And then my increments, I'm going to be going by ones because that's the length of each rectangle. And then let me go to second graph to get my table. So at -2.5, we have the value 6.625. After that, 3.625, 1.625, and 0.625. So starting with 6.625, we had our values that go with each of these middle x values. And at this point, I just have to add some rectangle areas together. So my first rectangle had a base of 1 times this height, this middle height of 6.625. And I'm saying my integral from -3 to 1 of f of x is approximately equal to this and some other stuff I'm about to write. But you do need to write approximately equals because this is an approximation. We know it's not the exact value. So next, I've got a base of 1 times this height of 3.625 plus a base of 1 times height of 1.625. Same deal over here, 1 times 0.625. And I'll just add these all up. You could leave it unsimplified and call it a day, but I'm going to add it on the calculator. So here we are on the calculator again. To save a little time, I multiplied each of these by 1 in my head. I'm pretty good at multiplying things by 1. Pressing enter, about 12.5 for that area. For this one, I'm trying to figure out the area under this line on the interval from 3 to 5 with 4 subintervals using RRAM. Let me start by making a table of the endpoints for each of the rectangles that I'm going to be using here. So we're going to be starting at 3, the leftmost endpoint, and since I'm traveling a distance of 2 for the whole interval using 4 subintervals, that means each subinterval, each rectangle, has a base of 0.5. So after 3, the next endpoint is 3.5. Then we've got 4, 4.5, and finally 5. Let me just plug all these now into my function to figure out my y values that go with those. And I'll use the calculator table function for this. So here I am in my y equals. I just plugged my function in as y1. And now I'm just going to look up some values in a table. Let me do second window to get table set and set the guidelines for my table. I want my table to start at 3. I don't care about anything before that x value. And my table values should go up, my x values should go up by 0.5. So let me put that in as my delta table. And then let's just go to second graph to get that table. So at 3, I have an output of 2.5. Then it's 2.25, 2, 1.75, and 1.5. So going from 2.5 to 1.5, these are just the values from my calculator here. I'm just putting them here so we can look at them. All right, so now let me create my rectangle areas. So my integral from 3 to 5 of f of x is approximately equal to the following. I have, for this rectangle, a base of 0.5 times its RRAM, so we use the right height endpoint here, 2.25, plus Next one, we have a base of 0.5 times this height of 2. Then 0.25, or 0.5 rather, times a height of 1.75. And finally 0.5 times a height of 1.5. You could leave it like this or plug it in your calculator and see what it adds up to. I will do the latter just because I like getting final single answers. And to do this a little more quickly on the calculator, I've essentially factored this common base of 0.5 out of all of these. And I'm just adding up the things that it was multiplied by in a parentheses next to it. So this comes out to 3.75. On this problem, they want us to approximate the integral from 0 to 27 of this function with some table values here using RRAM. So I'm going to say that this integral is approximately equal to the following. So for our first rectangle, we have a base of 7 going from 0 to 7. And we're going to use the right height because this is RRAM. So the choice between 6 and 8 for the endpoints, we're going to go with 8. So we have 7 times 8, base of 7 times a height of 8. Plus, the next rectangle has a base of 6 from 7 to 13 and a height of 9. After that, we have a base of 3 times a height of 6, a base of 5, height of 4, plus this is a base of 4 now times a height of 5, so that's cute. And then after that, we have a base of 2, height of 3. You could leave it like this or simplify it on the calculator. Let me just go ahead and see what this all comes out to. When I plug all of that in the calculator carefully, I end up with 174 as the final output. For this problem, I'm trying to approximate the integral from 0 to 44 of the function represented by this table. I'm going to be using LRAM for this one. So these are all endpoint heights of rectangles in this f of x row. I'm going to be using the left one for each rectangle. So we can say that this integral here is going to be approximately equal to, and now here's the area of my first rectangle. I have a base of 10 from 0 to 10 times a height of, this is LRAM, so I'm going to use 5 rather than 6. So base of 10 times a height of 5. And again, I'm approximately equal. I know this is not the true value, so I'm spelling it out that this is an approximation. All right, so the next one, we have a base of 5 going from 10 to 15, base of 5. Height of 6, and we're adding all these now. Next, we have a base of 6 times a height of 4. After that, base of 4 times a height of 2. And then from 25 to 43, that's a base of 18 times a height of 3. And then finally, a little jump here, 43 to 44, base of 1 times a height of 2. And let me just plug all this in the calculator if I'm curious what the final result is. So plugging all that stuff in, let's see what it comes out to. For what it's worth, 168. There we go. On this problem, I'm trying to figure out the integral, the approximation for the integral of f of x from 0 to 34, using just the values in this table. And I'm approximating that using left rectangles, LRAM. So let me set that up now. We've got this integral approximately equal to, and now I have some areas here, base times height areas. My first rectangle has a base of 3, going from 0 to 3, and it's got a height, since this is LRAM, it's got a height of 11. We use the left height here. So 3 times 11, and notice that I wrote approximately equal to. Next, we have a base of 11 going from 3 to 14, so base of 11 times a height of 14. Next, we have a base of 1, height of 17, plus a base of 10 times a height of 18, plus a base of 6 times a height of 19, plus a base of 3 times a height of 20. And you can leave it that way or add it up on the calculator. So if I carefully plug all that in and press enter, that comes out to 558. On this problem, I want to approximate this integral using RRAM with values from this table here. So let me go ahead and set this up now. I'm going to be doing base times height rectangles, and I'm going to use the right height on each rectangle because this is RRAM. So I can say integral from 0 to 22 of f of x is approximately equal to, and here's my first rectangle area, base of 2 times a height of 5. And after that, from 2 to 7, that's a base of 5 times the right height here of 7. Next, we have a base of 3 times a height of 5. Base of 7 times a height of 3, base of 3 times a height of 4, and a base of 2 for this last one with a height of 3. So you could leave it like this, or if you want to add it on the calculator, let me do that now. So here we go, plug in all this in. Let's see what it comes out to. 99, almost 100.